Now, this was one question of a comprehension section that involved some graphing, but it involves the radial field produced from a current carrying conductor and combining it with another magnetic field. This time, it's combining with the Earth's magnetic field. And we are told to not worry about the actual direction of the Earth's magnetic field. We are told here that it's known to be 5 or 50 microtesla, so 5 times 10 to the negative 5, and to be considered horizontal. Because remember, our little compass is on a horizontal plane. It can only align itself with the horizontal component. So yes, we might know that the Earth magnetic field at Perth is a bit stronger and 66 degrees above the vertical, but we're just aligning itself with the horizontal. Now, we also need to know that the wire is aligned north-south, and when current passes through the wire, it's passing in such a way that beneath the wire, the compass then aligns itself in the net magnetic field. That means that it's aligning itself with both the Earth, which we know travels north, horizontal, but now the wire must be producing a rightwards. Now, which way must your thumb point such that below your thumb, your fingers are pointing to the right? Down the page. Now, that's one of the early questions here. Draw the direction of the wire current in the wire that would produce that deflection. Okay? So now what we're going to do, we're going to pass 5 amps through, which would produce a magnetic field. But the aim of this is to determine mu naught. We know that the current through the wire can be explained as mu naught I over 2 pi r. But in this experiment, we don't know what mu naught is. There's another way to figure it out. If we know the Earth's magnetic field, Alex, yes, what is it? I don't know.
What is it?
It's forces on charged particles. I added it there, but you've got a paper copy, so worry.
Yeah, I'm just wondering.
Okay, worry no longer. The Earth's magnetic field. And we have measured the deflection angle. That's literally the angle of the compass needle from where it would normally like to point north. That way, if we measure the deflection angle, then we can figure out that the current from the wire is B tan theta. Okay? And that's good because we're just measuring theta and we're measuring R, and then we can determine B, so we can determine mu naught. Now, here is our table of data. All you needed to do, I've already sort of solved it. I just simply went 5 tan 0.4, calculator spits out 2. So that was one of our empty cells that we had to fill in. Over here, we had to take the inverse of that and express it using the same significant figures. So 6.7. I don't really care too much about that unknown because you guys can do that in your own time. Now, here is the thing. If I go back to this equation, to get it in its linear form, we're going to go B equals mu naught I over 2 pi times 1 on R. Look at that. That's going Y equals mx. All right. So if we plot the field strength of the wire against the inverse of 1 on R, because obviously what was happened, I should have mentioned, what was happened as you lower the compass, the magnetic field produced by the wire gets weaker, and so it aligns itself more closely to the Earth's. So as you increase the distance of the compass, then the wire's magnetic influence on the compass is less. And we should see that in the data. Let's have a look. As we increase the distance from the wire, we should see that the deflection decreases. Okay, and again, if we set R to infinity, that's like removing the wire completely, then the deflection would be 0, because now it's the only external magnetic field is due to that of the Earth. Now, in the lead up to your SIS test, which is next term, we need to bring in the idea of error bars. Now, the question has come up, error bars will not feature in the mid-year exam, but we will teach it in term 3 and we will assess it in the SIS test, and it may appear in the trial exam because it has appeared in past waste exams. in a variety of different ways. Sometimes they give you the graph with the error bars and you have to play around with it. Or sometimes they give you the error and you have to plot a graph with the error bars included. Sometimes it's just one axis, so sometimes it's just vertical error bars. There was one year where it was nasty. They had both error on the X and the Y, so you had to plot horizontal and vertical. So it's important that we cover it. We have the time to look at net magnetic fields, which you guys were all terrible at, and linearization of data, which you're pretty good at. Now I want to introduce, let's consider error in this activity, okay? So I'd like you to consider that there was an uncertainty of plus or minus half a centimetre in this measurement, okay? So it was measured with a ruler with a certain uncertainty, in which case I'm just going to squeeze in a percentage uncertainty, because here's the thing, guys. If I had a measurement here of 0.050 plus or minus 0.005, well, it could be as high as that or as low as that. We can't just invert the uncertainty, because what's going to happen? Your error would be flipping huge, yeah? So what we're going to do is express it as a percentage. And then this measurement would have the same percentage error, okay? So we can't just go the inverse of 0.005. It's not 20 plus or minus 2,000. Right? That's not how error works. But we need to express it as a percentage. Some of these are easy and I should be able to do in my head. That's plus or minus 10%. This is plus or minus 10.0%. Plus or minus 5.0%. This one here would be more 3.3. This one here would be, 1 point, thank you. This one here would be 2. And then I think this one's like the 1.7. Cool. Okay. Now really, if we could have gone error on, but I believe this was a mid-year exam and we hadn't yet done error bars. If this was a end-of-year exam, I would have put in an empty column next to it and asked you to determine the percentage uncertainty. And then over here, I would like the absolute error of 1 on R. So I should be able to do most of that. You might want to help me, or I've got my calculator. What's 10% of 20? Well, that's plus or minus 0. No, it's not. It's plus or minus 2. What is 5% of 10? That's plus or minus 0.5. Help me out here. 0.22. 2.5, so 5 times 2.5 on 100 is, now we're going to go, we have to round it to the same sig figs, or the same decimal, so we'll go 0.1. This one here is also going to be 0.1. And then I think the last one is also 3.3 times 1.7 on 100 is just rounded to 0.1. Now, I made up this uncertainty, right? It might be a little bit tricky, but obviously if this was going to be in your exam, we'd work it and make sure that you could physically draw these error bars and everything could be drawn precisely on the graph. So, over the page, hang on, let's not go over the page just yet. Let's just figure out a couple of things. My buddy dimensional analysis should help us out here. But first off, I want to know what the SI units for the Tesla are. So I'd go F equals BIL. So B equals F over IL. Okay. If you have some scrap paper, just scribble this down. Well, what's that? That's a Newton over a Coulomb per second meter, which could be Newton meter second per Coulomb. That's a unit for the Tesla. But really, we know that a Newton is a kilogram meter per second squared over the SI units for current, which is Coulomb per second, over the SI unit for length, which is the meter. And so we can cancel out And the unit for the Tesla is a kilogram per kilogram per second per coulomb. That is the derived unit of the Tesla. It comes from the fundamental quantities of mass, time, and charge.
M-1 on top. And M-1 as C-1. And M-1.
Up here?
Yeah.
Okay, thank you. I didn't really want that because I want what the actual... I'd rather these ones are a bit better. Okay, but thank you very much. Okay, now, what we then want is to figure out what the units of mu naught are. So if I've got B equals mu naught I over 2 pi r, well, if I rearrange for mu naught, what would we do? We'd go B times 2 pi r over I. Now let's throw in our units for B, which was kilogram per second per coulomb. R is meters. I is coulombs per second. And look what happens now.
We're just ignoring the 2.
We are ignoring the 2 because it is dimensionless, and we're also ignoring the pi because it is dimensionless. And we've got a coulomb -1, so we get kilogram per coulomb squared meters. That is our unit of the magnetic constant. Not very helpful. Over the page, we are soon going to plot magnetic field strength in Tesla as a function of 1 on R in per meters. Okay? And we're expecting linearized data. So your gradient could just be simply Tesla meters. Sorry, let me just quickly sketch rise over run. Tesla over the inverse of meters. Your gradient should be Tesla meters. Or we know that a Tesla is that. So we could then go, well, it's actually, a Tesla is a kilogram per second per coulomb times meter. So again, you can expand out your units, kilogram meters per second per coulomb. Do you know what your data sheet has for the... let's just jump straight into the graphing because I think I've just overwhelmed you all with...
Velocity times mass.
It's...
Momentum. Coulomb.
Well, no, I was actually going to ask for the the magnetic constant is kilograms per amp squared, but it gets a little bit hairy. Could we please get over to the graph? The table is incomplete. We have completed those values. Now, I'm actually going to plot this because I want to show you how to correctly draw these error bars. So, our field strength needs to go from 0 up to 2. So, you might want to choose a nice scale step on your y-axis. Maybe 0.25, 0.5, 0.75. Okay. And then your R values. Now it turns out this is not the best scale step to do, but I'll show you the error that Mr. Murray made after telling you that there's an error. Just go with that flow. So I'm going to quickly grab some... No, I don't have it, so I'll just quickly start plotting. So 20 to 2, that should be right at the top. Ten goes to 1. Oh, that's nice. So if you could do this, please, in the next 5 minutes, I will also go 6.7 goes to point... Oh, look at that. It's a direct relationship. That's handy. I could just draw anything along these axes. Here you go. No, I better not. Let's Let's plot the data.
When you say
5 to 0.5, yes. What?
units like kilograms, meters per second per coulomb, is that momentum per
No.
charge?
Ooh. Oh, no, don't do that. No, it's not. No, it's not momentum per charge. That's, no. 4 goes to 0.4.
Well, why not?
Because it's not. Because it's not. It's not. Please don't. And 3.3 goes to 0.3. You're upsetting me, Rahul.
So,
Now, I noticed that all of that data was perfectly proportioned. So any variance in that is my inability to plot on the graph. My inability to plot data. Okay. Well, I can see straight away that data has been plotted incorrectly, so I'm just going to move it. You can't do that, but where was it? 5? No, 6.7. Now, gentlemen, could you get to this stage? Plot your data, please. Yeah, I mean, if you want to cheat, you can just go from 0 up to that corner. Yes. But I need you to plot the data, because the next thing I want you to do is to plot in our horizontal data bars. And you will see in a moment the reason why I should have increased my scale step, because I don't really want my error bars up here. Each line is, plus or minus 2. I just realised I've forced every single kid to draw a bad graph because they would have copied my scale step. Off the page. Next, plus or minus 1. Then I have to revert back to my 6.7 plus or minus, 0.5, not 1.
I don't know. No, you don't.
So now each tiny line is 0.2 horizontal. So to get to 0.5, I need 2.5 bars. Then for my 6.7, it's 0.2, so that's 1. And then down to 0.1, it's literally going to be half a line either side. So this is where you need to have very sharp pencils to draw in your error bars. Now, in reality, I would pick an error that would enable students to draw this clearly. So when I just chose the absolute error of my measurement of distance, obviously the inverse of that, it gets a little bit too small. Could you please get to this point?
Where there's no uncertainty in the
So for now, we're going to ignore any uncertainty in B. But in reality, who asked the question? Who asked the question? The vertical? In reality, both measurements of the dependent and independent should have their own associated uncertainty. But as you can see, if we start adding both error bars, it gets a little bit messy. It gets a little bit difficult to work with. Okay?
You basically like an error box.
Yes. And we will look with, there's a booklet that we've made up that we'll look at next term on how we can use error bars to determine uncertainties of our measurement. So again, this is 10 bars long, this one is 2.5, that's 1 bar long, and then these are both half and half and half, because that's 1 per meter, 2 per meter, 2.5 and 10. Oh, sorry, 20. No, 2.0. 2.0, 5, 2 and 1. Who has finished? Hands up. Cool, that's enough of you. Sorry, we're moving on. Let's complete the question as it were. So, this is why I'd ask you to draw the error bars first, because I don't want you getting your gradient lines in the way. So if you ever get a question that has error bars, now we can pick an area that's out of the way, that isn't going to interfere. So, oh gosh, why isn't it crossing? Ah, it's crossing right there. Oh. Ah, there's no nice intersection. No, I like to live dangerously. Let's do it. So this is 16, comma, don't know. No, I do know. It's 0.80. And then this guy here is 8, comma, 0.80. Up here is going to be 16, comma, I don't know. Yes, I do. It's 1.6.
Do we need the third point there as well? The third.
Well, I do for my rise over my run. Yes.
But the third point.
Maybe you just need 2. You don't need that one?
Yeah, do we need that?
Wow, okay. So, 16 take 8 was my x's. And then I had 1.6 take 0.80. And really, again, if you went from the origin to that top corner, your gradient should be 1 times... Oh, look at that. What is this? This is just 1 times 10 to the something. What is it? 1 times 10 to the negative 6? Yes? My brain's not working. Can somebody... It is? Right. So now, we've got the gradient. Guys, this is going to be such a common thing. It's plot the graph, determine the gradient from your linearization, figure out your unknown. So on the previous page, we said that if we wrote it like so, let me get rid of the fun stuff, which is the answers. Don't spoil it for everyone, Mr. Murray. Oh, no. All right, so if we wrote out our magnetic field strength like so, that's the gradient. So therefore, mu naught equals just rearranging that.
Just right-hand gradient, or can we like abbreviate to M?
Yeah, that's fine. If there's no symbol in there that's going to confuse you. We had our current controlled as a constant 5 amps. And you get pretty much pi times that. You're going to get the answer that's in your data sheet. You're going to get 1.3 times 10 to the negative 6. Which when compared to the data sheet is 1.26 times 10 to the negative 6. But this was to 2 sig fig. So we're pretty good. That data was like spot on. Show you're working. And in fact, that's all that you needed to do. That was it, the answer. But I just thought we'd quickly compare with what was actually given in the data sheet. You get perfect data. And if you're expressing it to 2 sig fig, so it comes down to how well you plot your data. If you plot your data a bit shoddily, your gradient might be a little bit low, in which case you might get 1.2. So maybe the marking key, because the known constant is 1.26, if you went a little bit too shallow, you might get 1.2. So we might allow 1.2 or 1.3. Okay? And that's it. Done. You end up getting to 3 sig fig, it's 1.26. Your error percentage is, what's your percentage error? 0. If your measured is your accepted, then you are spot on the answer. But here's where I want to take this question further. So are we all ready to do so?